hundreds of miles up. Satellite images are basically our eyes in the sky for everything from tracking massive storms to understanding climate change impacts.
Right.
But the sheer volume, the complexity of this imagery,
Yeah.
well, it often means that getting really specific answers from AI has been surprisingly tricky.
Precisely. Yeah. Imagine you need to quickly identify, say, bridges damaged after an earthquake, or maybe pinpoint areas where deforestation is happening fastest based on some very specific criteria you have in mind. Current AI models often struggle with those kinds of user-defined, reasoning-based requests, especially when you apply them to the intricate world of satellite imagery.
Okay, let's unpack this because that's exactly where we're headed in this deep dive. We're zeroing in on a fascinating new AI model called LISAT. That's LISAT.
Right, language-instructed segmentation assistant for satellite imagery.
Exactly. And our insights today, they come directly from the research paper that introduces this new approach.
Yeah, and our goal really is to understand how LISAT can take these complex natural language instructions, the kind of queries a human analyst might actually pose,
Right.
and use them to not just identify, but precisely outline specific objects, specific areas within satellite images. It's really about pushing past the limitations we've seen in earlier AI models in this critical field.
And those limitations are pretty significant, aren't they? The paper makes it clear that analyzing satellite imagery isn't really the same as looking at photos taken, at ground level.
Not at all.
You've got incredible visual clutter, objects that could be microscopic or, city-sized, and then those really subtle visual cues that carry a lot of meaning.
Yeah, absolutely. Trying to tell a small car from a building rooftop from space, that's a serious challenge for an AI. And what's made this even harder is the relative scarcity, you could say, of high-quality training data that pairs these nuanced natural living queries with really detailed annotations in satellite imagery. That lack of specific data has been a major roadblock in developing more intelligent systems.
So let's dig into why those earlier models haven't quite cracked this then. The paper highlights that many current segmentation models for remote sensing, they're really good at identifying things they've been specifically taught to recognize.
Yeah,
right?
exactly, like predefined categories.
But when you give them a more open-ended query, something that requires some level of reasoning or understanding context, well, they tend to stumble.
Yeah, and what's fascinating here is the difference from how we analyze, say, regular photos. A model might easily spot a dog in a picture, no problem.
Sure.
But if you ask it to find all swimming pools without safety fences in residential areas in a satellite image, well, now you're asking it to understand concepts and relationships, not just recognize predefined objects.
That's a great example.
The paper's examples, things like identify flood-prone urban areas or which regions have observed urban expansion, they perfectly illustrate this need for that extra layer of contextual understanding.
And it's not just about the complexity of the questions themselves, is it? The paper emphasizes that satellite imagery itself throws a unique set of, curveballs at these AI models.
Oh, definitely. Consider the sheer scale. A small boat might be just a handful of pixels, right?
Okay.
While a major port could dominate the entire image.
Huge difference.
And those subtle visual differences are absolutely crucial. From high above, a patch of bare earth and maybe a construction site might look deceptively similar. The AI needs to pick up on very fine-grained visual cues combined with the context from the query just to tell them apart. Plus, the relationships between objects in a vast satellite scene, they can be much more complex and spatially distributed than in your typical ground-level shot.
It's interesting, too, that even the more recent geospatial foundation models, the ones that have made progress in understanding this kind of data, like RSGPT-4V and EarthGPT.
Yeah, the big ones.
They still have a key limitation.
Okay.
The paper points out that while they can generate text, they can describe what's in an image or answer questions about it.
Which is useful, of course.
But they can't actually produce those critical segmentation masks, those precise pixel-level outlines of the objects we're actually interested in.
And that lack of precise segmentation, that's a real bottleneck for so many critical applications. Think about disaster responders needing to know exactly which buildings are damaged right down to the pixel level.
Or urban planners needing that precise boundary.
Exactly. Or urban planners needing to map the precise boundaries of new developments. Textual descriptions, they provide valuable information, sure, but they just don't give you that crucial spatial accuracy needed for many real-world tasks.
Okay, so we've laid out the challenge pretty clearly. Now let's talk about the proposed solution. LISAT.
Right.
The paper introduces it as an open source and open data vision language model, a VLM, specifically built to handle these complex remote sensing tasks, understanding image content, answering questions, and crucially, precisely identifying and segmenting objects based on natural language instructions.
And the fact that it's open source and open data, that's a really significant point, actually.
Why is that?
Well, it means the research and the underlying technology are accessible to a much wider community of researchers and developers. It allows for broader adoption, scrutiny, and, further innovation in the field. LISA aims to be a kind of foundational tool.
Gotcha. And as in these paper highlights, LISAT's core mission is basically to bridge that gap we were talking about.
Yeah.
It's connecting the advances we've seen in AI's ability to reason about and segment objects in more general contexts with the very specific challenges and the growing demands for sophisticated analysis of our planet from space.
And a crucial element, really, that allows LISA to do this so effectively lies in the new specialized data sets that the researchers meticulously created.
The data. Always comes back to the data.
Absolutely. They recognize that the existing training data just wasn't sufficient to teach an AI to perform this kind of nuanced reasoning and precise segmentation in the geospatial domain.
Right. They developed two key data sets, and the first one they emphasize is GRES, the Geospatial Reasoning Segmentation Data Set. This sounds like a real cornerstone of their work.
It is indeed. GRES contains over 27,000 carefully annotated instances across more than 9,000 satellite images. And it's specifically designed for this task, this reasoning-based segmentation and remote sensing, where the natural language queries directly refer to single specific objects within the image.
The paper mentions it's semi-synthetic. Okay, let's unpack that. Where did this crucial training data actually come from then?
So they started with a foundation of the BivView dataset, which is a large collection of high-resolution satellite images that already had bounding box annotations for over 60 different types of objects.
Okay, existing data.
Right. But to create GRES, they took this existing data and applied a really clever filtering and generation process.
A clever process involving quadrants and focusing on what they called unique and interesting objects. Tell us more about that strategy.
Exactly. So they divided each image into 4 quadrants. Within each quadrant, they then filtered the detected objects to identify those considered unique.
Meaning not many of them around?
Right, meaning there was at most one other object of the same class in that quadrant. And interesting, meaning that the object class itself wasn't overly common across the entire FEFU dataset.
Oh, okay.
This helped them select objects that were more likely to require specific disambiguation in a natural language query. The key insight here, I think, is that by focusing on these less common and more isolated objects, they could create training examples that really pushed the AI to understand the subtle visual differences based on language.
That makes perfect sense. You want to train the model to really focus on the specific characteristics of an object that make it distinct from everything else around it.
Precisely.
But how do you go from those bounding box annotations to the detailed pixel-level masks and those natural language queries that describe them? That sounds like the really complex part.
Okay, here's where it gets really interesting. For generating the natural language queries, they leverage the power of a large vision and language model, specifically GPT-4V, through a clever 2-stage prompting approach. First, they showed GPT-4V just the cropped image of the object within its bounding box and asked it to identify unique visual features, things like its color, shape, texture, any distinctive characteristics.
Just focusing on the object itself first.
Exactly. Then, in the second stage, they showed the model the entire satellite image, along with the locations of all the detected objects, including their target object, and asked it to generate a full natural language query that would unambiguously identify that specific object within the broader scene.
So they were essentially tasking the AI with describing the object in a way that would make it crystal clear which one they were referring to, even amidst all the other visual information, like giving directions.
Precisely, yeah, like very specific directions. And for creating those detailed pixel-level masks, they used a model called GeoSam. They ran it in a high-resolution configuration to get a very fine-grained segmentation of each object within the bounding box, and then they further refined those masks to ensure accuracy. And to make the training data even more robust for each initial query they generated, they then asked GPT to rephrase it in 2 different ways.
Oh, interesting.
Yeah, giving them a total of 3 diverse natural language queries for every single annotated object in the GRES dataset. This ensures the model learns to associate a single visual object with a variety of ways it might be described in natural language.
Wow, that's an incredibly sophisticated process to build this GRE's dataset.
Yeah.
It really highlights the importance of having exactly the right kind of training data to tackle this challenge.
It was absolutely crucial. And that's not all. The second major data set they developed is called pre-GRACE.
Pre-Grease,
And this one is on a whole different scale. It contains over 1 million question-answer pairs.
1 million.
Yep.
Okay, that's a massive increase from the focused annotations in GRES. What kind of data makes up this larger pre-Grease dataset?
So pre-GLES is designed for multimodal geospatial pre-training. Think of it like giving LISAT a broad education in understanding both satellite imagery and the language used to describe it before it specializes in the reasoning-based segmentation tasks defined by GREs.
Sort of like a foundational course.
Exactly. It's an aggregation of existing remote sensing datasets that cover a really wide range of tasks.
Okay, so it's like giving LISAT a strong foundational understanding before it dives into the specifics. What are some of the different types of data included in Pregress?
Well, it includes image captioning data from several datasets like NWPU captions and RSICD, which provide detailed, long-form textual descriptions of various types of top-down imagery.
Okay, descriptions.
Then there's visual question answering, or VQA, data from datasets like RSVQ, AHR, and FloodNet. Here, the AI is trained to answer questions about aerial and satellite images, covering things like identifying objects, understanding scenes, even assessing damage after a disaster.
Right, like answering specific questions.
And finally, it incorporates visual grounding and region-level captioning data from data sets like DIOR, RSVG, which helps the model learn to associate specific words and phrases with particular locations and objects within an image, linking language to place. So this diverse pre-training is really key to giving LISAT a strong baseline understanding of the geospatial world.
So it's a really comprehensive collection of data aimed at teaching LISAT to understand both the visual content of remote sensing images and like the nuances of the language we use to talk about them.
Exactly.
That pre-training on Pregressed must be a significant factor in LISAT's impressive performance then.
Absolutely. It provides a strong initial grounding. And when we look at LISAT's internal design, its architecture, it builds upon this robust data foundation by integrating a powerful multimodal large language model with a sophisticated segmentation model, drawing inspiration from a prior model called LISA.
So what are the key components here? What's actually working behind the scenes in LISAT? What's under the hood?
Okay, so at its core is a multimodal LLM based on Vicuna 7B, which is a very capable language model. To process the visual information from the satellite images, it uses a remote Slipley VIT L14 encoder to extract the relevant visual features.
Got it. Vision encoder.
Right. Then, a linear projection layer acts as a kind of bridge, aligning these visual features with the language model's internal representation of text.
Connecting vision and language.
Exactly. This pre-trained combination of Vicuna and the remote SLP encoder trained on that massive Pregress dataset is what they actually refer to as LISAT pre.
Okay, so LISAT pre is the foundational piece, the brain, maybe. What about the part that actually does the segmentation, the outlining of the objects?
Right, the drawing part. For the segmentation aspect, LISAT utilizes a decoder based on the Segment Anything model, or SAM.
Ah, SAM. Heard of that one.
Yeah, it's pretty well known. And they've implemented a really innovative technique called the embedding as a mask paradigm. Think of it this way. They've added a special new token to the LLM's vocabulary, specifically to represent a request for segmentation. A special token, like a command.
Kind of.
Right.
When the model needs to generate a segmentation mask, it produces this special token. And the internal representation, the embedding of this token, is then directly translated and fed into the SAM decoder, essentially telling it where and what to segment.
Oh.
It's like the language model is directly communicating the segmentation instructions via this special embedding.
So the language model is essentially using this special token to directly tell the segmentation model, okay, outline this part of the image. It's a really elegant way to connect the two parts.
It is, yeah. It's quite neat. And the entire LISAT system is trained together end to end. They first pre-train LISAT pre on the vast Pregress dataset, and then they fine-tune the complete LISAT model on the more specific GREs dataset, as well as some additional natural image segmentation datasets just to further enhance its capabilities.
Okay.
And the training process uses a combined loss function that encourages the model to both generate relevant text and produce accurate segmentation masks, balancing both tasks. All right, so we understand the problem, the proposed solution in LISAT, its crucial training data, and its architecture. Now for the big question. How well does it actually perform in practice? The paper highlights some pretty impressive results.
It does indeed. Yeah, the results are quite striking. In terms of understanding and describing the content of remote sensing images, LISAT outperformed existing state-of-the-art geospatial foundation models like R's GPT-4v by over 10% in BLU4 score.
Okay, 10% on BLEU4. And that measures description quality,
Yeah,
right?
it essentially measures how well the AI-generated descriptions match human-written ones. So a 10% jump is quite significant. It indicates a substantial improvement in the quality and relevance of LISAT's textual understanding of the images.
That's solid. But what about the segmentation, the core task?
Right. And even more impressively, on those critical remote sensing reasoning segmentation tasks, the ones where it has to understand a natural language query and then precisely outline the requested object, LISAT achieved a remarkable 133% higher GIU compared to previous top-performing open domain models.
Wow, hang on. 143%.
Yeah, 143.36% to be exact on the paper's numbers.
That's not just a small step forward. That sounds like a massive leap in performance.
It absolutely is. GIOU, or Generalized Intersection Over Union, it's a key metric for evaluating the accuracy of segmentation masks. A 143% increase signifies a fundamental shift in our ability to precisely identify and understand features in satellite imagery based on natural language.
Yeah, you can see how that would be useful.
Think of how much faster and more accurately disaster responders could operate with that level of precision.
Definitely.
And what's particularly encouraging is LISAT's strong performance when it comes to identifying smaller objects in satellite imagery. The paper includes a detailed comparison, Table 2 specifically, and it clearly shows that LISAT exhibits larger relative gains in accuracy, especially for these smaller, more detailed features that are so crucial in many remote sensing applications.
So it's good with the small stuff, too.
Exactly. This directly addresses one of the key challenges we discussed earlier, that issue of varying object sizes in satellite imagery. It seems LISAT is significantly better at picking out those smaller details when guided by natural language.
That's fantastic. And the research also looked at how LISAT's performance improves as it's trained on more data, right? The paper mentions something about scaling behavior.
Yes, yeah, that's in Figure 4. Their experiments showed a clear trend, increasing segmentation accuracy as they increased the amount of training data from the GRES dataset.
Makes sense. More data, better results.
It does, and it suggests that with even larger and more diverse datasets in the future, LISAT's capabilities could be further enhanced.
Interesting.
They also experimented with using different base segmentation models, SAM versus GeoSAM, and found that surprisingly, while GeoSAM was specifically designed for geospatial data, using the original SAM model actually yielded slightly better results in this context.
Really? Why would that be?
Well, the thinking is maybe SAM's broader training on a wider variety of natural images gives it a more adaptable ability to extract visual features, which benefits even specialized domains like remote sensing. Sometimes general knowledge helps.
That's a really interesting insight. It highlights how sometimes a more general model, trained on a massive and diverse data set, can actually outperform a more specialized model, even in its own specific domain. And going back to the pre-training on pregress, it sounds like that really paid off as well.
Absolutely. The paper highlights that LISAT-Pre, the pre-trained backbone, achieved top-tier performance on several key image captioning datasets. It outperformed both previous models specifically designed for geospatial data and more general-purpose vision language models.
So it's great at describing things.
Yes, and it also demonstrated strong results on visual question answering tasks, particularly in its ability to determine the presence of specific objects and make comparisons between different elements within the imagery. So, across a range of fundamental tasks, that pre-training proved highly effective. And the ablation study they conducted, where they systematically tested the impact of different components.
Taking bits out to see what happens.
Exactly. That really solidified the effectiveness of their chosen components. Remote CLIP as the vision encoder, and Vicuna as the language model for this particular domain of remote sensing.
It really paints a picture of a thoughtfully designed and highly effective model. However, the researchers are also pretty transparent about the areas where LISAT still faces challenges, right?
That's right, and that's good science. No AI system is perfect, and it's important to understand the limitations. The paper points out that LISAT can still struggle with very heavily clouded images where the underlying features are obscured.
Makes sense. Can't see through clouds.
Right. It makes it difficult to identify objects even with a clear natural language query. It can also have trouble when the query is quite vague and could potentially refer to multiple similar objects within a complex scene. Disambiguation is hard.
Needs specific instructions.
Yes. They also noted that in some instances, the original ground truth masks in the GRES dataset, which were generated by GSM, might not be completely accurate themselves. And this can sometimes lead to LISAT being penalized in evaluations, even when its predictions are actually quite reasonable.
Ah, so the measuring stick itself might be slightly off sometimes.
Potentially, yeah. It's a challenge in creating these large datasets.
So there's still work to be done in handling those more challenging visual conditions and in refining both the way we formulate our queries and maybe the quality of the training data itself.
Definitely.
What kind of future directions do the researchers envision for LISAT then? Where does it go from here?
They suggest several exciting possibilities for future work. One key area is scaling LISAT to be able to process much larger, full-resolution raster images, which are the standard format in many remote sensing applications.
Handling the really big pictures.
Exactly. Another is exploring the integration of LISAT with other types of segmentation models beyond SAM and GeoSAM, perhaps looking at more specialized architectures designed for specific types of geospatial features.
Tailoring it further.
Right. And they also see significant potential in incorporating multimodal and hyperspectral data sources. That kind of data could provide much richer information content for the model to learn from and reason about, more than just visible light.
It sounds like LISAT is not just a finished product, but really a strong foundation upon which a lot of future research and development can build.
I think that's a great way to put it.
Now, beyond the technical advancements, what kind of real-world impact could a model like this have? The paper touches on this in its impact statement.
Yeah, the potential impact is really broad and could be, well, transformative across several critical areas. Imagine disaster management teams being able to quickly and easily ask the system, okay, identify all blocked roads in the Western District, and immediately receive a precise map highlighting those obstructions.
Instantly seeing the problem areas.
Exactly. That's the kind of rapid, actionable intelligence that LISAT could enable the ability to get specific answers, both textual and spatial, from complex satellite imagery using simple natural language.
That's a really powerful example. So we're talking about potential applications in everything from environmental monitoring, maybe tracking deforestation or changes in ice cover.
Absolutely. To urban planning, search and rescue operations, even more efficient agricultural monitoring. The list goes on.
Basically, anywhere you need specific info from overhead images.
Exactly. The ability to rapidly and accurately extract specific information based on natural language could really revolutionize how we understand and interact with our planet's changing landscapes. The paper also briefly mentions, and it's important to note, the potential for misuse in surveillance applications.
Ah, right. The dual use concern.
Yeah, but they emphasize that their research is based on publicly available data sets of cluttered scenes, not focused on tracking individual entities, and they strongly encourage responsible development and deployment of this technology.
Okay, good that they acknowledge that. So to bring it all together then, what's the core message from our deep dive into LISAT today?
I think the key takeaway is that LISAT represents a really significant step forward in AI's ability to understand and interpret the complex visual information contained in satellite imagery, all through the intuitive interface of natural language.
Making it easier to talk to the data.
Precisely. It has demonstrated remarkable progress in describing images, answering questions, and, crucially, performing that reasoning-based segmentation with a level of accuracy that just far surpasses previous models.
That 143% jump really sticks out.
It really does, and the fact that both the model itself and those valuable GREs and pregress data sets are openly available provides a fantastic opportunity for the broader research community to explore, build upon, and further advance this exciting field.
Absolutely. It's inspiring to see this kind of progress in making AI more accessible and, well, capable of understanding our world from that global perspective. And it really makes you think, doesn't it? What new possibilities might emerge as AI becomes even more adept at understanding our geospatial world simply by us asking it questions in plain English?
Yeah, what happens when understanding satellite data is as easy as having a conversation?
It's definitely a fascinating area to watch. What are the ethical considerations we need to keep front of mind as this tech gets even better? Lots to think about there.